Hi there. Okay, welcome to lesson 5. This is to do with composition of functions, and really what that means is we are going to combine functions one after the other. We're going to do something to x with a function, and then whatever we get, we're going to do something else to that by way of another function. So let's look at an example here of the first part here. It's saying when a pebble is dropped into a pool of water, ripples in the shape of circles form on the surface of the water. The radius of the outer ripple is given by the formula. Let me just cancel that. Given by the formula, radius equals 0.3 t, where t is time. And that's talking about in seconds. If the area of the circle is a equals pi r squared, which we know already, combine this formula with the radius formula for the outer ripple to write a formula for the area of the circle after t seconds. In other words, what we're going to do here is we're going to combine this equation here and this equation here. So it's a combination of functions, and we'll just move the cursor there. Okay, so we want to write a formula for the area, it says here, the area. So we know we can start with area equals pi r squared. But we want a formula for the area of the ripple after t seconds. It's got to incorporate this value t into an equation for area. Now notice this does not have t in it. However, if we use this value here for r and substitute it in here, we can rewrite this a different way with t. So we're going to replace r with 0.3 t. Oop, sorry, I should make that t. I'll get this eraser here. Okay, I'll just get rid of that. Okay, so t, 0.3 t. And then r was squared, so we have to square this. And that's basically the answer. So we combine these two equations, and we've got this new equation which does incorporate time. So moving on to the second question here. It's talking about Toyota Camry has a fuel efficiency, does 8.2 liters is consumed per 100 kilometers. Cost of gasoline is $1.25 per liter. The volume of liters of fuel used can be written as a function of the distance. Okay, how many liters equals something incorporating the variable d? L equals so many, d in other words. So 1 liter is equal to how many d? Well, we've got a ratio here. 8.2 liters is equal to 100 kilometers. We really want to say that a liter is going to get us so many kilometers. When we think about this, it's 8.2 liters is equivalent to 100 kilometers. We could divide both sides by 100 and say that 1 kilometer is equivalent to 0.082 liters. And that's exactly what this is asking for. Now let me just pause. So for every 1 kilometer traveled, we'll use up 0.082 liters. We can just say here that the liters used, L, will be 0.082 liters every kilometer times kilometers, or times d for distance. Now as we travel 1 kilometer, we'll use up 0.082 liters. If we travel 100 kilometers, if d is 100, we'll use up 8.2 liters, and so on. Okay, so that's one function. It's a function using d that will equal liters. We've written this in distance, and our answer is in liters. Moving on to this one, the cost of gasoline used can be written as a function of L. Cost is a function of L. Well, we know that the cost is $1.25 per liter. So if we use 1 liter, the cost is 1.25. If we use 2 liters, it'll be 1.25 times 2. So simply the cost is going to be 1.25 times L, however many liters we use. Okay, let me just scroll down here. So we really have two equations here right now. First of all, let me just say that we had L liters was equal to 0.082 times the distance in kilometers. We also had the cost, and that was 1.25 times the number of liters used. Now notice we can write the cost in a different way. We can substitute in our value for L here, this value right here, into this equation, the second equation. So the cost will equal also 1.25, and then substituting our value here for L, 0.082 times D. So really we've used a combination of functions here. This is what this question is asking. We can find the cost of gasoline in terms of the distance traveled by combining these two functions above if we substitute the formula for the first into the formula for the second. So that's what I've done. We've written C as a function of D. Right here, C as a function of D. And here we have it right here. So we can write 1.25 bracket 0.082 D. Okay. Now, investigating the, let me just read this. When two functions are combined in this manner, we say the new function is a composition of the other two functions. I typically say combination, but composition of two other functions. Okay, finishing off this page, it's saying here to consider the function given by h of x equaling to 2x plus 3. This function can be thought of as being composed of two functions. Simply we multiply by 2, we take x, we multiply by 2, and then we add 3. Two functions. Multiply by 2 function is denoted by f, and the add 3 function can be denoted by g. What they're saying here is that we take x, if we multiply it by 2, that function is simply multiplying by 2. And another function is taking this value, in other words, this is an input value, f produces an output value of 2x. Another function will take this value, which for it will be its input value, and simply adding 3. So if we apply one function and then the other to x, we end up producing 2x plus 3. So they've taken certain values and shown you what happens along the way. If you have 0, by doubling it, multiplying by 2, you get 0, and then adding 3, you get 3. That's the final output. If you take 1, you double it to get 2, and you add 3 to get 5. If you start with an x value of 2, you double it to 4, add 3 to 7. So this is showing you here basically what it's saying. The function f applied to x maps to or gives you an output value of 2x. So what does f do? It is equivalent to taking x and multiplying by 2. You can write f of x equals 2x. The function g takes 2x and changes it to 2x plus 3. So simply all it does is add 3. In other words, if you take 2x, you end up with 2x plus 3. Or another way to write that is that if you take g of x, you end up with x plus 3. Here we took 2x and ended up with 2x plus 3. If we just started with x, we'd just be taking x and adding 3. So in fact, this is the actual equation for g of x, because it adds 3 to whatever value you had. Okay, we'll pause there for part 1 of this lesson, and I will resume with part 2.